Hello friends, welcome to our YouTube channel RF Design Basics. Today we are going to start a new subject, that is electronic material and devices. We will start this subject with introduction of semiconductor material and semiconductor devices. We know the materials can be divided in three categories. Insulator, semiconductor and conductor. First one is insulator. Example of insulators are glass, plastic, mica, woods, etc. Insulators are very bad conductor of current, that they don't allow any flow of current through them at any temperature or any voltage. Second one is conductor. All the metals are good conductors of electricity. And the third one is semiconductor. These semiconductors are not fully insulators or conductors. These semiconductors are the elements whose conductivity lies between the conductivity of metals and in that of insulators. The electrical conductivity of any material is denoted by sigma. This is electrical conductivity. And this is ability to conduct the electric current through the material. So sigma for insulator is very low. Electrical conductivity for insulator is very low. The value is 10 to the power minus 18 to 10 to the power minus 8 Siemens per centimeter. And electrical conductivity for the conductor is very high. The values are 10 to the power 4 to 10 to the power 6 or 10 to the power 8 Siemens per centimeter. This semiconductor material has a very unique property, that its conductivity can be varied between the conductivity of insulator and that of conductor. So how the conductivity of semiconductor can be varied? These semiconductor materials are very sensitive to temperature, optical illumination, electric and magnetic field, and minute amount of impurities. So increasing or decreasing the temperature will affect the conductivity of semiconductor, or optical illumination or applied electric and magnetic field will also affect its conductivity, and the amount of impurity, we call it doping, that will also affect the conductivity of semiconductors. So this sensitivity in conductivity makes semiconductor one of the most important materials for the electronic applications. Example of devices that can be made with semiconductor are diodes, transistors, switches, sensors, lasers, solar cells, digital logic circuits like logic gates, amplifiers, oscillators, and many more. Now we will study about the semiconductor materials. Here I have written few elements from the column 2, 3, 4, 5 and 6 of the periodic table. Semiconductor materials can be elemental semiconductor or compound semiconductor. There are two categories, elemental and compound. Elemental and compound. Silicon and germanium from the column 4 of periodic table are called elemental semiconductor. Elemental semiconductor, silicon and germanium. These two elements, silicon and germanium, are called elemental semiconductor because it consists of single species of atom. Consists of single species of atoms. And compound semiconductors are combination of elements from the column 2, 3, 4, 5 and 6. These are combination of elements from column 2, 3, 4, 5 and 6. Now we will see where these materials are used. This germanium was used in early days of semiconductor development, but nowadays silicon is the most used semiconductor material. Why silicon is most used semiconductor material? Because of its better thermal stability, it is stable at even higher temperature, its easier availability, Silicon is abundantly available on earth, and because it is easily available, it has lower cost and easy process also. So due to these factors, silicon is most used semiconductor in the semiconductor industry nowadays. This compound semiconductor is used where high-speed devices are required and where emission or absorption of light is required. So first one is where high speed is required, high speed devices, and the second one is where the emission or the absorption of light is required. Now we will see few examples of compound semiconductor. Suppose we combine gallium and arsenic from column 3 and 5. So it will make gallium arsenide. Gallium arsenide. In same way we can make gallium phosphide and gallium nitride. These three are common light emitting diode. Few more examples are zinc sulfide, indium antimonide, cadmium selenide, lead telluride. There are many other examples. This zinc sulfide is used in fluorescent material in TV screen, and these three are good photodetectors. And many more other combination of these elements are possible to create a compound semiconductor. Among all the compound semiconductors, this gallium arsenide is most used compound semiconductor and is commonly used in devices wherever the high speed is required. Now we will see a brief introduction of semiconductor devices. Whenever we say semiconductor devices, we mean electric circuit component made from the semiconductor materials. So these semiconductor devices are electric circuit components made from the semiconductor materials. The semiconductor devices can be of two types. First one is single or discrete devices. Examples are diodes and transistors, single or discrete devices. Or we can say single discrete devices. Examples diodes and transistors. Other one is integrated circuit. You have heard this name, integrated circuit. Also called ICs. So what are these ICs? These ICs are set of electronic circuits that consist of two or more single discrete devices. Examples are microprocessor and microcontrollers. And these ICs are etched on a small flat piece of semiconductor called IC chip. Nowadays, very large scale integration, VLSI, very large scale integration is used for chip making, and this very large scale integration allows to fit more and more transistor on single chip of the same size. And we can say a modern chip may have many billions of transistors in a single chip that is size of a human fingernail. This advancement of very large scale integration, or we can say this digital revolution, follows Moore's law. What is Moore's law? Moore's law. In 1965, Dr. Gordon E. Moore presented a paper predicting that the transistor count in a single IC chip would double every 2 years. So the Moore's law says transistor count in a single IC chip would double every 2 years. And this prediction is very much accurate today and is expected to continue for next few decades also. And with this very large scale integration, the devices are reducing in size and also the operating speed of the devices are increasing. So this was the brief introduction of semiconductor materials and semiconductor devices, and in next lecture we will study about one of the most important characteristic of the semiconductor, that is energy band gap. Thank you.